right, good afternoon. So let's start. Now we come to the final component of this course. So we talked about big data, things post-relational database, some topics like that. So we have been preparing for the last module. We talked about distributed systems, processing that area. Now we look at handling and managing the big data using database technology. All right, so the final component I tried to run that in two parts. So today we try to understand in a more general way about what is data model and what's really the problems with the relational database model and what kind of new models people are looking at. Okay, so more general aspect of NoSQL. And then next week, we will look at more concrete systems, different type of systems people know already, right? Like MongoDB and Hive and SAP HANA and so on. We're looking at actual systems. So not this one. All right, we have it. So today we look at what's the motivations and then what's the requirements, okay, for non-relational systems. And we're looking at NoSQL systems, but many prepare for the foundation. We leave the actual systems to the next week. All right, so the number of systems, if you are following what's happening in the industry, for job interview, things like that, you probably have heard about systems in this column a lot, okay? Before these systems, what we have is really relational database systems, okay? And after the relational, people proposed all sorts of different systems. Key values databases, sometimes people simply call the KV system. What are they? And then what's the document database? And what are the column family stores? Sometimes they call column databases. They're slightly different. We will look at that. And also, today is getting more and more popular. It's called graph database. So for graph database, we're not going to introduce actual systems, but we just give you some general idea. So what is NoSQL, right? Initially, people simply, a bunch of programmers, they believe that the relational database is already, that's the end of it, is already, used by time, already expired. So they simply they say, we have a system called NoSQL. NoSQL means no relational database, right? As strong as that. And indeed, they threw away relational database system completely. They built everything from scratch by themselves. Okay? And after a while, this system getting into use and so on, people become more politically correct. They say, oh, no, we didn't mean no SQL. We mean not only SQL. All right, sounds slightly better, but a lot of people still call it NoSQL today. Although officially they call that not only SQL. So you add things beyond relational systems. So what is NoSQL is a collective name for many things we mentioned here. They all call it NoSQL. It's a collective name for these database or data management technologies which are beyond the relational model. Okay. So in terms of course, there are many different types of NoSQL systems. But in general, they share something in common. First thing they have in common is non-relational. All right. So I don't know what kind of things come to your mind when we say non-relational. Okay. Non-relational. So relational comes first will be something table, right? So not necessarily a table. Okay. And relational, of course, comes into mind with a lot of constraints, integrity constraints, right? Not necessarily we have constraints. And of course, we don't have a non-procedural language such as SQL, right? So and of course, not necessarily we support asset property, the transaction property, we don't. So if you're talking about the relational database, all these things comes with that immediately, right? Schema, normalization, constraints, asset property, SQL language for declarative query processing, right? So when you have non-relational, all these things, we throw them away first and see whether we can survive. And then typically, because they do not build anything based on MySQL or Oracle, anything like that, they build from the ground up. So a bunch of programmers, software engineers, they want to find the easy way and more efficient way to handle their data. Right. So typically they build from ground up to handle so-called new data challenges. We'll look at what are they. Right. And it's good news. Most of them are open source. Okay, sponsored by different companies sometimes, but all open source. Many of them are actually Apache project. That's a very key motivation, right? This technology comes behind after MapReduce, Google File Systems, HDFS, right? Those kind of technologies in like 2004, 2005, and for NoSQL technologies comes in 2009 and 2010, right? So already after 5 years, already after massive deployment of these cluster-based systems, right? So they find that if you really want to manage your data using relational technology on top of cluster systems, it's very hard. So they want to find something cluster-friendly, all right? And also, they don't like schema. Relational database people really, really like schema, right? What is schema? As simple as a table design, right? Of course, database is a collection of tables with referential integrity constraint and so on. But in general, it's table design. So what's wrong with the table design, right? What's wrong with design the format to represent your data before you actually upload your data, right? For relational database, of course, we got used to that. You have to design the table before you load your data there. But then this bunch of programmers said, no, we cannot do that. Why? Because our data change so frequently. We roughly, more or less, we're dealing with this type of data. For example, a customer in our e-commerce company, right? Customer is a customer, but customer will not have a rigid set of attributes like a student or bank customer. They are customer from anywhere. They can be identified with different information. And for different customers, we probably capture different information. So in that case, a schema becomes a burden, right? So they said schema less. We don't use schema. And when you throw away schema, of course, all these beautiful things, right? Data integrity check, all these constraints, all these things gone as well. But they are willing to do that, right? So schema less. And eventually, they know that transaction processing is important to many applications, to banking and many other applications. And people spend a lot of time to get that things right and reasonably efficient. But it turns out to be too slow for many online applications, right? Which they said, we don't really care about this consistency, concurrency control. If we have some redundancy, if we have some inconsistency, let me deal it in my program. As a system, you don't have to worry about it such that you can run faster. Right? So this slide's got a lot of information there. So each of them, I hopefully can look at that. You can come up with something to explain what they mean. So what is non-relational, right? Why ground up? What they mean by cluster-friendly, what's the motivation to have a scaleless schema, and what kind of gains they get, and what kind of losses they make. Right. And then why they don't want to acid property. Right. But anyway, these are those things in 2009. Right? People started from these kind of motivations. Just like those people find the era for relational database gone. Today, when we're looking at this set of requirements, many of them are not applicable either. So this area, NoSQL, is continuously evolving. We have new techniques, new technology developed all the time. Right? So in this course, it's not about using a system, develop your application using these systems. Is not as such, right? Rather, we try to help you to understand all the motivations and give you a good view about landscape of this area, right? So such that, hopefully you're better positioned when you see new systems. In the next couple of years, when you start to work, I'm pretty sure they have new systems coming all the time. So hopefully we are better positioned to understand these kind of things. In order to put this big no in front of SQL, and of course you need to say how bad SQL systems are, right? Why they're not good, right? And of course you need to understand what they can offer, why they are good. And then things are very interesting. All the things we say they are good, actually it turns out to be against them very soon, right? And all these things that turn against them, and later, after a while, they said, oh, actually, that's what we want, right? So this kind of spiral things. Relational database is good because it's a plug and play, right? You buy, you purchase, you download, and then you can basically use it no matter what kind of things you do, right? It's actually quite a sophisticated piece of technology. And for people with some IT background, actually it's quite easy to use, right? So there are a lot of proven technologies in terms of millions of users use at the same time. They never make any error in terms of ACID, consistency and so on. It is a persistent data, right? So this is very important, and people also complain about that, right? You have data in your program, in Java program, but they are not persistent. And so a lot of data you actually want to put into some kind of data management systems to do that. And then this interface, as we look at them later, this interface actually is a mismatch. The way you handle data in your Java program, for example, and the way they store data in the database actually are very different, right? So persistent data storage is what they can offer. The persistent really means persistent, right? We know that durability in ACID, right? We have D. D means durability. Durability, that basically means whatever happens, whether it's a machine failure, whether it's concurrency, whether some people just bad, try to destroy things, whatever, it's persistent. That's very good. They took a lot of things away from your application programmer. So that's beautiful property, concurrency, no matter how many people update, no matter what kind of sequence they do, there's a goalkeeper there, which is DBMS, right? You access data through DBMS. DBMS have a very sophisticated transaction management system, right? They schedule this thing such that they're always correct, right? The concurrency is not a problem. Data integrity, data integration, they are all good. And then standard data model is a table, right? Normalized. Everybody understands it. A lot of properties comes with it. So that's good things about that. But why these things become bad? So the first one I just mentioned, this is a mismatch between how data are stored and how data are used, right? So there were some figures. Now, if you are a database programmer, you probably use ODBC, use Oracle Core Level Interface. There are a lot of APIs provided by relational database for you to use, right? And typically, you will open the database connection, right? And then once you have that table, you define cursor. Right? This cursor can move around, tuples, next one, or whatever, or search to locate the cursor. And once you locate the cursor, you start to read the tuple, and then you do some transformation, either data types or do some pre-processing, and then to load this data into your object, say Java object. Okay. And then they said, actually, for all the program, this is very tedious work, but 30% of your time actually is doing these kind of things. And again, when you want to write your data back to the database, you do the same thing. Right? You do the same thing. You still need to, you cannot write this object, say object person, into this database. You cannot do that. You basically still need to put a part of that into part of column and somewhere. Okay? So this kind of is a mismatch. In your program, in your whatever language, Java program, right, you deal with some kind of cursor. You process data one by one. Okay? So it's individual instance is what you're looking at. Right? And for relational database, the whole data is a set. Right? Whole data is a set. Okay, there's no sequence, no order, not really individual things. And things are not linked together. These things all, database can do that for you, but you need to look at these issues. Right? So this kind of called impedance mismatch is intrinsically just not matching. Right? People don't like it. Who don't like it? Programmers don't like it. Right? These people will spend a lot of time doing this translation and say, why should we do that? Okay? So this every record, is a tuple or instance is the way you, as a programmer, you deal with anything, objects you have. And the relational database, we only deal with a set. Right? They are mismatch. As I mentioned, if we as a database designer, we tend to put data into different places. This is what we call normalization. We tend to put data in different places. But when you need to retrieve data, for example, we will have an example later. You are a customer got a lot of information, right? If I'm a programmer, I would like to have a customer with all the information about this customer available to me, right? And then if you store this customer information into a relational database, you will put something here, something here, something there after normalization. Why? You want to avoid the redundancy. You want to avoid all this update anomaly, all these kind of things. But it is still your job to linking these things together. That's, again, quite annoying for some people. They say, why? Why should I do that, Some people can benefit from that. For many applications, they don't really care about it, but still they're going through the process. So that's one reason people really don't like relational database. Okay, in particular, software developers, they don't like it. Right? These kind of things, like set-oriented is not the way we deal with data when we write our code. In addition to this problem has been around forever. Right? In the 70s, people started to complain. In the 80s, people started to complain loudly. And then there's one technology people tried and failed called the object-oriented database. Right? They want to organize everything as object. Object write to disk still as object, and you retrieve as object. So object will be the common things, like Java object. So the common thing, you organize data in your program, and you organize data on your disk as well. People really tried. And they even have a lot of commercial systems available. Right? This problem, they didn't really solve the problem because once they really looking after needs from programmers, from database point of view, they don't know how to store them. They don't know how to index them. The things will not become scalable, and no transaction processing will not be able to do it, right? So people tried and failed. But that's an old problem, very well known in the 80s even. But then people get a lot of new problems. You say, wow, all my new data, right? New data types come all the time. Applications are very different. Some care about transactional properties. Some simply do not. Okay? And then there's different new programming paradigms, and in particular, those based on MapReduce Hadoop. Clusters, data are massively distributed. Relational database, yeah, we tried, right? We did. We talked about distributed database. It's not really scalable, okay? And then you can go to GFS or Hadoop file systems, but they do not support any data structures as such. It's a plain file system. Right? So from this, people start to say, no, it's time for something new. So in 2009, a bunch of Hadoop programmers, they meet. They talk about need to have a complete new way to eliminate all these problems that, they really hate, right? And at that time, they already have something called Google Big Table, right? Big Table is not, it's not really database systems, but it's closer. Comparing to file systems, it does looking at some kind of structure, right? They support what they call semi-structured data. So they want to look at something like that. So they have a bunch of criteria they put together, all right? So these people said what name they should call it. They should call it obvious, everybody understands it, has not been preloaded with any meaning, and once people see it, people will be shocked by the name. So they end up with something called NoSQL, right? They serve that purpose. And what is that? We're open source. There's a bunch of programmers, right? They're not Google programmers. They are a bunch of programs. They want to have an open source. Everybody can use it. And they want to distribute it. They can handle clusters, computer clusters. And they are very clear. We don't want relational. It's too restrictive. So this is what open source distribute non-relational systems, all right? So they want to be able to run this with computer clusters, but there are things involved. Even like today, on a single machine, people still use NoSQL system, right? But initially it was designed, or the attempt to design this for computer clusters, right? And then, we talk about graph model and different type of models we'll talk about later. They don't want a scheme because they say, number one, our data are not really structured or well structured, right? And number two, even their structure change all the time, right? So they want something called a schema-less, right? Then they become the whole area, technology. Now it's really mainstream technology now, and they change them to not only SQL, right? And then this become sort of independent of what they call polyglot persistency. That's basically independent of programming language you want to use. It's just a piece of technology to manage data. On top of that, they have a user interface, and any language you should be able to work with any systems, file systems behind. Right. So what are they exactly? All right. So they are motivated by aggregate. Right. Aggregated basically means putting data together. Right. So it's on the other side of normalization. Normalization, they want to put a piece of data into smaller pieces such that they satisfy all these kind of nice properties. First normalization, second and third normalization, and so on. And they want to do aggregate. Aggregate is from the user's point of view. Right? All the data I care, I want to store them together, and I can get them together. And if in a computer cluster system, they actually stored on the same cluster, for example. Right? So they talking about new data model. Last year, when I first introduced this into our teaching, I called them advanced data models, right? And this semester, I rather call them modern data models. Yeah, they are newer than relational, but by no means they're more advanced. Actually, quite the contrary. They are not advanced at all. Okay, they are modern, newer. So what is data model then? What is data model, right? We say modeling. We have a lot of data modeling tools. You remember any data modeling tools? How do we model our data? Relational, of course, we implement a model, right? Model can be conceptual, can be physical, right? When we do conceptual modeling, everybody knows ER, I hope, right? ER diagram is a way to model data. And of course, as a programmer, you probably prefer to use UML, right? That's another way to model your data. But in general, when you model your data, that's basically you have a data, all this data available. That's the subject of our study, right? But you want to have a data model, right? Data model is the way we perceive and manipulate data. Data is there, but we need to organize them in some way we can understand it. We can perceive them, right? So there will be entity, there will be relationship, and things like that, and some constraints as well, right? So the way you perceive data is part of data modeling. And also, more than that, the way you manipulate, right? So if we're talking about relational data model, that's a way to manipulate that, right? And later today, when we're looking at a graph data model, there'll be very different way to perceive data and to manipulate data. And by the way, it could be the same data, right? It could be same data. Same data, you could model them in a relational way, or use a NoSQL way, or maybe as a graph, right? But different way you organize it, they have different advantages and disadvantages. And different way you organize them, the way you manipulate data will be different. All right? Keep this in mind and see whether at the end of today's lecture you have better understanding of this. All right? So data model is data model, right? Data model is conceptual. How do we organize data? But then, underneath that, you have storage model, right? The data, once they are conceptual models, they need to be stored in some way, right? This is completely different. We don't talk about it. We don't talk, even in relational database, we don't really talk about storage model, right? Of course, it is important, right? We don't really talk about storage model, and we don't really talking about the way how do we use it in your program. So basically, once you get data into a program, you can do this in whatever way. We're looking at data model part, so not the storage, not the programming model. And today, when we're talking about data model, one thing we very well understood is relational model. Okay, relational model is the way to model data. It's a relational way. And the manipulation is a relational way, and typically using SQL. Right? So this is what we have. And then suddenly you have 4 different data models. That's what we are going to cover in this part. The first is key value and the document and also column. And this, we give them a collective name called aggregate model. Aggregate is not like a aggregate function in SQL. Okay? In this aggregate, just means putting all the things you see as related to each other together. Okay? So it's when we do relational data modeling, we looking at the proper way of organizing data. No matter who will use it, no matter how do you use it, I'm looking at the proper way to organize data. And by proper way, we mean normalization, third normal form. We want to remove all these kind of unwanted properties, right? We don't really care that much about how people use it. And this is very different. This is precisely focused on how people will use it. If we use this group of data together, we call them one aggregate, right? Maybe there are redundancies, fine, I don't care, because I want to use them together, right? So they call the aggregate model. And another model, slightly different, but now today is getting extremely important, is called graph model. We will discuss that as well. So we already mentioned what is aggregate. In relational database, we start with what we call universal table, right? We have a huge table. Everything of interest will be there. Very poorly structured, a lot of redundancy, and all this kind of thing. But you start from there, and then you start to do normalization, right? Number one, you do not want to have any nested structure, right? You have a name and the first name and the second name. We don't want that. Right? Every column is a column. There's no subcolumn in any column, right? So not nested structure. It's not like spreadsheet. Spreadsheet, you're afraid to introduce these nestings. No problem. We don't want that. Okay? So that's the first normal form. And then in order to remove this partial dependency or transitive dependency, as we studied before, right, we'll do further normalizations. And eventually, you end up with a bunch of smaller tables, and you say, I'm happy, right? Because all these unwanted properties are removed, right? So that's the way the one big chunk of user data will be put into proper places, such that it can manage with integrity constraints or can be enforced. But aggregate is different. Aggregate is simple collection, a collection of related data objects that's to be treated as one unit. And very frequently, we also call it document. called a document. You're thinking about that. It's just reverse, right? A lot of relational database programmers doing this report, right? Reporting. All these things, you write different report. For sales, for whatever, you write report. So the report is a collection of related information for some purpose, right? You imagine that. That is an aggregate. That is a document, right? So a report is useful for some people, so we can go in through this process to generate a report. And then for this aggregate model, say, oh, maybe a report is the way I store data, right? So that's the difference. So aggregate is a document, right? So in this case, table is no longer flat. Where I have a report, I can have nestings, right? Because people want to see that, right? So it's no longer flat, and attributes is not really atomic, right? Attributes can have sub-attributes inside. Aggregates sometimes, because it's a natural way of grouping data together, maybe it fits very well for my application, and also very importantly, because you are going to use the data in same aggregate or same document together. So this document that we use very frequently here is not like a text document, right? It's just a JSON object, if you know that, okay, or XML document, right? This is document. Document is everything put in together. If things together, it's a better unit or natural unit for data replication and allocation. That's the way we're putting everything together on this machine. I can process it on this machine. I do not have to. You can imagine if in a relational database and the part of the table is here and part of the table is there, and you want to join, very, very messy, right? And in this case, we do put all the relevant information in one place. Right? So this is called aggregate. So let's look at one example. Let's look at one example. So this is, don't worry about UML. I don't know whether we still teach that. We used to. But in general, there are some example of a simple database modeling. We have something called a customer. Right? Customer is an entity. Customer, you have your name and some other attributes. And we have another entity called product. Right? Product, you have the names and so on and so on. And the address is also one entity, one model. Right? And then what we do is we want to accept some orders. And orders, of course, one customer can put in many orders, multiple orders. And an order consists of two parts. So one part is they have in your order, you have a few line items, right? You buy this one, how many, this one, how many, how much, and so on. So an order actually is a number of order items, or called line items, right? And then, of course, when you have one order, you tell me how do you want to pay for it, right? Credit card or whatever. So this information is also relevant, right? Then eventually, order product, you say how many order, and for different customers, maybe I give a different price and so on, right? And then interesting thing here is address. When you have order payment, when you make an order payment, maybe a multiple payment for one order, right? And you typically give a billing address, right? So this address is maybe your home or your organization and so on. And then at the same time, for each order, you also have a shipping address. Okay, they both address, but not necessarily the same. We know that, right? You purchase from your office, and your shipping address your home, or you purchase that for your friend, things like that. Okay, so this is one application we're talking about. All right, and then with this kind of modeling, it's very easy for us to end up with clean and good relational database design. Right? Once you've done UML modeling or ER modeling properly, we do the database design in a simple way. Right? If we end up with customer table, about basic information about the customer, and basic information about product, and also you have an address. You can imagine you have a list of addresses. Later, people, when you see what's your address, you do not input your address, rather you choose ID of the address. Okay, because I have complete piece of addresses. And then you start to talk about order which customer, where to ship to, right? So this is very simple. But what items are actually included in that order, right? We have a separate database called order item, right? So all the ID integrity constraints in foreign key point to this one. So when we, and the product is a foreign key point to this one, and price is unique to this one. And then in order to find an order a customer made, right, I couldn't find it from here. I have to do a number of things, right? I need to join all the order items with the order ID. So in order to find all these items containing the order, right? And for this order ID, and then I have product ID, probably you want to have product name instead of product ID, which doesn't make a lot of sense to a lot of people. So you also need to join this table with the product, right? And then when you have this address, you simply use address ID. This customer, this billing address is this address ID, right? So we have a single address database. So that's the relational database design and properly normalized. And here I just added a slide today to give you some kind of instance, right? And the color are a foreign key relationship, right? So purple refers to purple and blue refers to blue. Okay, so I uploaded this already. So this is a way, but it doesn't really matter how we design that, right? What matters is that, as you can see, all this, for me, I started with doing one thing, right? I really want to process the orders and so on, and I need to go through this normalization, modeling and normalization, eventually end up with this bunch of tables. And then from this bunch of tables, if we want to find information for one order, not a single place can give you anything. You need to join them together based on this color-coded foreign key relationship. Okay? All right, that's what we do. So that's the relational stage. And now we want to manage this object. So we say, look at, all this design, what we call, they are normalized and they have referential integrity constraints, right? But when we, as a programmer, when we deal with this bunch of data, we probably care about, I want to deal with customers. So all the information about this customer should be together, put into one place, right? I don't want to do join to find them. That'd be too hard. Right? Or, the way I see things is order. So I want to find the information about order altogether, right? That's what we want to do. And you're thinking about that. In your customer, right, you have a customer, you have a number of billing addresses. Okay. And when you have an order, each order needs to have at least a shipping address, right? And then when you have and one payment or number of payments, and for each payment, you also have a billing address, right? So this address, the three addresses, so if you aggregate these things together, you will have, in one logical unit, you want to say, okay, if this is the way you organize data, you will find this address actually are duplicated, appear here and here and here, right? And then there's no such thing called ID and you do join. That's the way we do it in relational system. And in this case, you do not do that. You simply say, oh, it says address, I have address string there. Or this address, I have an address string there, right? That's the way we see data, right? But if we do that, in a single logical address record, they appear 3 times, right? If it is an aggregate model, we don't want to do join. We don't want to use ID to join with another table in order to find the address string. Rather, we simply copy them. We simply copy them in the place they should be. I'll show you an example next slide. This is fine if your address do not change, right? If they do, and then you have to change many places, and you probably don't even remember what other places this address appeared. Okay. So is that a problem in relational database? No. Relational database, we don't have redundancy, right? The same address only appear once, and everybody use ID to refer to that. When I need to change address, we change address. And once it's changed, everyone, when they need this address, they will use a new address, right? We have so many properties to ensure that, everyone will see the new address, right? So it's good. No redundancy, so no update errors, these kind of things. But the cost is you need to join them. And for these people, they don't want to do that. They say, if my address, once you give me a ship address, it's not allowed to change. If this is my business logic, not allowed to change. And then why should I do that? Why don't I just copy the address in this aggregate such that I avoid join, right? I avoid these difficulties in distributed processing. All right? So that will be something they call it aggregate. That's why we call it a document. It is document, right? In this case, maybe this, in the back, you can use relational database to store them differently, but then this, get data from different parts. But that's what we try to avoid. We know the beauty of this, and we also know the cost of this linking data, right? And what now we want to have is a document. Document with all these values actually copied there, all right? Maybe redundancy, maybe not the best way to model data, but that's the way I use it. I want to do it in that way. Okay, so that's why we call this is aggregate, right? This is aggregate. You get data from different places, right? And this is logical units. They have some meaning there, right? So this is called an aggregate and also called a document, right? So aggregate or document is the foundation of NoSQL processing. We don't have something called table anymore. All we have is document, okay? Well, can you give me a design methodology so with this data, I know what will be the best way to model that in documents? We do have that for relational database, right? Once you know all the attributes, you know all the constraints, you follow the methodology. We have ER diagrams. Once you have ER diagrams, we have mapping rules, right? And eventually, we also have a theoretical guarantee with normalization. So we have a proper design methodology for you to do it. Do we have the same thing? To guide users to do a proper document-based data store design? No, we don't. All right. Some people initially say we don't need it. Of course, it would be nice if you have that, right? So you don't. So how do you define aggregate? Depending on how data are used. So this is interesting. The way to organize data is no longer a property of data. It is a property of the use of data, right? So in the past, when we do relational database design, you give me the database. We pretty much, database is designed for reuse. Database is designed for share, right? People with all sorts of different applications, they use the same data. That's why we want to have a database, right? So we really support a diversified range of data. So in that way, we separate data with data use. We focus on data itself, and the best way to organize data is a property of data. That's in relational domain, right? But now, it's different. How you organize data totally depends on how you want to use them, right? And then, if people want to use the same data in a different way, you organize them in a different way. We don't really share with them. It was okay, if Google, they do this page ranking, right? They crawl a lot of web pages. The only thing they do is page ranking. They don't do anything else. So why should they design database such a nice way in case other people want to use it? No, there's no such a case. Only used for that. Right? So that use is pretty much limited, and then we can optimize our storage based on that use. Right? But if your finance data, banking data, all this kind of data shared by a lot of people, and then we don't want to do things in that way. Okay? So that's very important. Relational database aggregate ignorant. which was indeed a very big advantage, right? But tend to against that. People don't want that, right? They want to be aggregate aware, right? So many advantages. I hope you can say a few, right? If I ask you what are the advantages, for aggregate ignorance, right? I'm pretty sure you can say quite a few things, but there are problems, right? They have costs to putting this together to generate the aggregate, and if it's in distributed environment, that's horrible. Cost is very large, right? So we don't want to use relational data, right? We want to use a document model. We only support one or very small number of applications. We know what's the best way to use the data, so we want to optimize our design to support this kind of use of data and also support processing a large amount of such data in a distributed system, right? So that's what we do. And then people start to propose two other advanced, so-called advanced data models. First one is called key value model, and another called document model. All right. By this time, document, I hope you already understand what that means. Both of these databases, they store them as a list of aggregates. Okay, they store them as a list of aggregates, right? And each aggregate got an ID. At least got an ID, right? It's something you got to have a name. And this ID is also called a key. So what is value? Key value store, right? Key is ID. Value is the document itself, right? So this is called a key value store. So key value store is very simple. In the key value store, they really goes to extreme. You see, everything got ID and some data. This data, I don't have any internal structure. I don't understand anything. It could be a picture, could be a movie, could be all the information about one customer, but is what we call blob. Binary large object, right? In Oracle, the Oracle term called blob. In Oracle, you can always create a column called blob. If you really don't know how to deal with that, you can store document, you can store web page, you can store movie, whatever as blob. Blob basically is a pointer, point to a file, right? Whatever there. You deal with it in your application. For me, I don't understand it. Right? So this is called the key value store. Key value store is really the only common denominator for many applications. We used to so at least we try to use table as the common things for support all the applications. And you telling me table is not good enough, right? So what is good enough? What is good enough is so flexible, all these new data types coming all the time. So what kind of things you want? You want ID and a blob, right? That's all we have. Okay, whatever you put inside, nothing to do with me. In this case, no schema. Redundancy is kind of, we don't talk about it, right? So this is called key value. It's very flexible. In what we store, you can put everything. It's just a container, right? Everything you can put into that. And in the same key value store, you can put something like a multimedia object, a movie here, and next you put all the information about customer, and next you put all the information about song or book. That's okay, right? You do not need to have any consistency between things you put into that, right? If you do have some consistency, we call that schema. We actually got data type, right? We say, value of that type. We don't have that. We simply use a blob, right? So very simple. Flexibility in what they store. And of course, they cannot support much, right? If it's movie, should be play or search or document, different thing, I don't understand it. I only support one thing, which is lookup. You give me ID, I give you object. That's all I do. And a lot of programmers feel this very happy. I have Java object dump into that area. I remember the ID. Next time I get the ID, I get the object back. Well, I do it by myself. So that data store does look after a few things, right? They look at data persistency, will be stored there. And also the data can be distributed in different places, right? And at least there's an ID. ID you can find in the back later. And also they go a little bit further than that. And typical key value stores, they also do this hash kind of indexing-based lookup. So lookup can be very efficient. Persistency, is looked after. Data distribution replication is looked after. And efficient data lookup is looked after by such a store, right? But the really minimum functionality. So this is what we call key value store. And of course, such a value part, blob, can be very large, right? And then if you use key value store, you give ID, the whole object reading to a program, and your program actually understands the structure, right? And then you say, oh, I actually have an object class. This name means this part, this name means that part. They got some structure in my program. I can use it later, right? But the cost will be you have to get everything into your memory, even you just need a little part of that, because the system doesn't understand it, right? For relational database, we understand it. If you want an address, I give you an address. I don't give you anything else, even there are many attributes, right? Because I understand what you mean. But in this case, key value store, I don't understand anymore, right? You get everything in there, and you pass it, you find the structure, and you use particular part you want, right? It's not good. People say, no, that's silly, right? That's silly. Can we introduce a structure into this value part? We do not see this as a blob. Rather, we have some structure. Okay, what's the structure? Structure you define as a user. And then this is structured value part we call document. Document, as a JSON document or XML document. A document is a collection of name-value pairs, right? So in this document, for this part of the data, you have a name. For that part of data, you have a name. And you can retrieve only that part of data using that name. You don't have to retrieve everything, and in your program to do it. Actually, we can support you here slightly better, right? But remember, this is not schema. This is not schema because the first object, I could put this kind of structure. And the second document, I put a totally different structure. That's all fine, okay? And some systems require a little bit of consistent document structure because they can be more efficient. That's getting close to relational database now, right? So you can see they go, first step is very far, key value, no structure. And then they go document store. Document store, typically a document also got an ID, so you still have a key value, but in this case, value is somehow structured, but flexible. Different documents in the same document store can be of different structure. And then people say, oh, maybe you should use the similar structures. And this is what I call schema. People do move into initially completed schema, and then they complete schemaless. And there are some systems called schema optional. From schemaless, they moved one step to called schema optional. So if you do tell me schema, I do better job for you. Right? And eventually, probably you go wrong. And of course, you can still define a schema. Right? So that's really very interesting and fascinating. And between the key value store and document store, there's no clear boundary. We said that we have these three ways of organizing them, right? So key value store, by this time you already understand it. Next week we'll look at some systems. And document store, I hope you also understand what is document, right? And also why people move from key value store to document store, because we want to have a little bit of structure, right? If these things are structured, and then we can use different columns to make that efficient. So that's a break, and start at 3 again. Okay, let's continue. Don't think we need another 4 hours for this one. All right. So we mentioned what is key value store in general, and also we mentioned what is document store and why we move from key value store to document store. All right. So what is document? This is document. All right. So I hope at least remind you something you're familiar with. A JSON document, XML document, right? A document is basically bracket and everything inside, content. The content maintains a very simple structure. The simple structure, basically, that's the name-value pair, right? You have a name, and there's a value, name, value. Remember, for addresses here, the value is a string of address. We normally do not use ID, these type of things, to link to other things, right? So things will appear here. The good thing about it is you can access this string directly. The bad thing about this, the same string may appear in many, many documents, and if you do update it, it can be quite problematic, right? But we assume updating is not really happening here. Okay? So this is document, very simple. And the third NoSQL data structure is called column family. Column family stores, okay? Column family stores is not column database. Column database today is very popular. CStore is a column database. Designed 10 years ago, exactly 10 years ago, by someone called Michael Stonebreaker. So I hope everybody already knows his name, right? The Turing Award winner this year. He designed this, it's called a CStore. So what is that? The motivation is that this is database, right? It's a table. He said the write is actually pretty rare, but some columns can be read very, very frequently. When do we have this kind of scenarios? We do not really write data very often, but some columns are used very, very frequently. Okay. So if you're looking at online transactional processing, OLTP process, that's not designed for that. OLTP, everything will be updated quite frequently, right? But if you're looking at data warehousing system, that's what we're talking about. Data probably uploaded periodically, once a day, once a week, right? So write is not very frequent, and even not overriding just to update, appending, right? But data analytics, doing analysis is very, very frequent. So today, a lot of people talking about data analytics. Data analytics typically can be characterized in such a way. Writes are rare and sometimes are append only, not overwriting data, right? But analytics are very, very often. So for this kind of systems, why relational database is bad? Okay. Relational database is what we call row store, right? A record is a row. This is a unit, right? No matter which attribute you need to fetch entire row from the disk first. And today, tables can be very, very fat, right? We have tables with hundreds, even thousands of attributes. And if they are one record, and there will be units to retrieve. Even you want one column, you need to retrieve everything. Even you will retrieve this column very, very frequently, you need to get everything out and then throw them away. Okay, so that was the basic motivation, is that no, we shouldn't store data in row order. The alternative is column order. So what is row order? Because although table is a two-dimensional thing, right? This is a two-dimensional thing. Everything actually written to disk at the end, right? Everything disk is a one-dimensional. You just write data on the disk. Okay. And when you write data on the disk, you have two ways to write it. And the natural way, what we always use and is already built in our way of organizing data is, here's a record, I write a record from here to here. Right? And second record, here to here. Because this is two-dimensional, I want to put them in one-dimensional, so I want to put them one-dimensional sequentially. One unit is one record, and then second record, and third record. Okay? So that's why when you read the disk, you find the beginning of the disk, the record, get everything in. Right? And then you locate a particular record, get everything in. Okay? So we don't even talk about it in relational database, but that's the way we store data. So here's two-dimensional table, and in row store, all this consecutive information, consecutive bits of a record are written together, right? And then followed by the next record and followed by next record. Okay, this is row store. So row order, every time you trip the entire row and look at the structure and return the attributes you want to you. Okay, so what is column store then? Column store says, I store all these attributes consecutively for all the records. Right? After all this, instead of different attributes of the same record, I put the same attributes of different records together. Right? So I want to put this together. This will be stored in that way, and followed by all the attributes followed by the next attribute for all the records followed by that. Okay. In this case, when you read all the attributes of all the values of one attribute together. In the past, we read all the attributes of one record together. Now, we read all the attributes for one column, different records together. Why? Because this column will be used frequently. So I want to read that. And I can safely skip a few columns if I don't need them. So in that case, this case is particularly good. It's particularly good if you have a very fat table and you only want to access a few columns, right? So that's why they use column store. But this is not good for updates. Why? This is not really good for updates. Why? If I want to change something, right? Change information about one customer, I read all your information out, I write a few things, and I write back, right? No problem. But now, if we column store, you change this attribute for this record, I need to find one column, entire column read, I change that a little bit, right? And then I found, you also change this, your age, and I found the age of 10 million people all reading, and change that a little bit. So it's not efficient for updates. But if you want to find the average age of all the students, that's easy. I read all the attributes in, and I do a sequential scan, I find it, right? I don't need to read every information, other information for anyone. I read all the attributes together, right? So that's a very controversial idea at that time, right? But it turns out to be extremely good for data analytics. But this is relational database. It's just different way to store the data for a table. Okay? And on top of that, still relational database design, attributes are fixed, still use SQL. Okay, all right. So that's the C store. Okay, I hope you got some idea. It's a kind of important concept as well. And then we also looked at Google Big Table now, right? When we say the three key technology from Google file systems, right? MapReduce, and another is Big Table. And for Google Big Table, we already know that they try to deal with some data which are sort of structured, but not the same structure, and most columns are empty. Right? They're semi-structured and very sparse data. And how they do it, they also have some kind of concepts called column family. Right? It's very simple. We already touched that in the last module. What they do is, number one, it's very much like a document store. Right? You have the first level of mapping, each two-dimensional. ID, document. ID, document. ID, document. These documents actually got some names called internal structures. You remember? We see content, we see which URL point to me and what kind of text they comment when they point to me, right? So there are some structures. So they have two-level structures. The first level, you have ID. In this ID, Google Big Table, of course, you see URL, right? Remember? URL is the way used because they designed that to store all the web pages. So they have a unique ID, and in Google Big Table it's URL, and they are sorted, right? They are alphabetically sorted. And then they point to something. Point to something conceptually, point to a huge, very fat, many, many attributes, a lot of information, right? But many of them are empty, and I don't want to retrieve all these things together, so I group them into families. Right? For example, this is for all content of the web page, right? And these are all the things in Chinese, right? This is all the Spanish, and these are the collection of all the websites which actually link to me, right? So you're grouping them together, right? They call them column family because you have a collection of related columns together, and actually not only conceptually they are related, and the Google Big Table also put you into some kind of physical implementation. Also, it's a small tablet for that, right? And of course, for each of them, you can have timestamp and so on. You can go back to have a look at a Google Big Table, right? So these are examples of family column stores. There are many of them, many of systems. We'll look at them later. Okay, but the list, I hope you. A little bit more things about column family. So, although, for example, if you're talking about a customer, right, a different customer got different information. For example, if you're a student bank customer, they record certain information. If you are retirees, and you record different information, right? Attributes are different, but conceptually, every attributes are there. But most attributes, this attribute is not applicable to you, this attribute is not applicable to you. That's why we call it very sparse, right? But conceptually, its attributes all there, right? So although different attributes, different tuples got different attributes, but in terms of the family, they're pretty stable, right? For example, your customer, you have something called a customer profile. But for different customer, for its retailer customers, right, you have an account, or just ad hoc customers, some customers, they all record the information slightly differently. But in general, there's a one category called profile, for example, right? And another category about orders. For different types of people, they probably different attributes to describe that person, so profile will be different, but they all have the same thing. So at the column family level, they are reasonably stable. Right. This column got this column family. So no matter what web page you have one column called content. You have one column called all the web pages point to me. Right? Maybe different things point to me, but we have this thing. So different rows typically have the same column families, but then the column family can have very different things depending on this object itself. Right? This kind of flexibility are there. So column families typically used for storage and access optimization. You retrieve one column family together, not the whole thing together, right? Because they are related, so when we retrieve together, that's efficient. And also when we do data distribution, we distribute each column as a unit, right? This is all pretty common sense stuff. All right, so before we talk about graph model, so that's going back again. Relational model there, not good, right? We want simple, we want flexibility, we want easy to deal with the cluster environment, we want to store whatever we want to store. Right? So the first step people do is use the only common denominator, which is a key and a value part, basically ID and the blob. Right? The blob is opaque. You don't really know what people put inside, but that's all up to you. Application can handle that. This is very nice, okay? And then people doing all sorts of different systems to support this kind of ID lookup very efficiently, whether alphabetically sorted with hash tables, right? And people have a disk-based implementation of key-value stores, and something called Redis is also quite popular in industry today. It's completely implementing memory, but the idea is the same. You use the simplest way to organize your data. Basically, it's ID and whatever, okay, called value. right? And then you go one step further, document store. For this value, it gives them some structure. Right? And then for many applications, the structure can be a large number of possible names, right? It's name pair, a lot of them. And then when you consider them as one big chunk, it's not efficient. So they have this column family design, right? They're grouping all these things together and store them physically together, but different column family of the same tuples could be stored in different places. So we talk about the three ways of organizing. There's three most fundamental ways to store data in NoSQL. And halfway we have a little detour about column store, right? Which is for different purpose. That's for support data analytics. It is purely relational. It's not NoSQL, but just all the data based on column priority. Column first, right? Get all the columns and then second columns. All right, so far we covered basic things about NoSQL, but then let's look at the other thing. All the three things, whether it's a key value store, or it's document store, or the column family store, they are all document models, right? They're all based on aggregates. They're all putting related things together in order to optimize the use, right? That's what I would say. The way to organize data, depending on how you're going to use it, it does not depend on how the data should be organized, okay? Rather the way they're used. Now look at something which are very different. So for NoSQL, there are two major models. One is the aggregate model. We already look at the three categories of aggregate model. And another model is graph model. Graph model is not talking about aggregate at all. Right? So what is that? So a lot of data itself is very simple. Right? For example, in social media, you are a user, okay? Because you have a Twitter account, so a user. So information about you is very simple, right? But the links, the connections among these users are very, very complex, right? And then you're thinking about if you are all these document store, they have a single origin of why people are doing that. They want to support e-commerce type of things, all right? They really to do e-commerce type of things. But if your motivation now is not care about e-commerce type of things, rather you do social media analysis, you want to find the people and people's relationship. That's one thing. And another thing is that I care about all the links among web pages. That was traditional application. Every web page is very simple, got a URL and a content. That's it. And then the links are quite difficult, complex. So I can point to other people can point to me. When I point to another person, I can add a label. I say this best Java tutorial. And then they point a link to my website. This is a pretty horrible professor or something like that, right? So they have this kind of things. You put a comment. They share something in common. The entity, right, you do is what we call node. Okay, a node. A node can be a person. A node can be a web page, right? A node. And then the interconnections among this node can have labels, can have meanings, right? And then we have a huge graph, right? And the question we ask is also very different. The question we ask is, do we have a common friend? Find all those people, you know, they are connected to each other with only two friends in between. We know 6 degrees of separation, right? 6, then everyone is connected. But we say, yeah, 2 degrees of separation, find all these friends. Or you find transitive closures. I want to find the friends of my friends. As long as they are my friends' friends, I want to find all of them. This actually is limited. It's a fixed point called transitive closure. But operations are very different from that. Okay, these kind of things are getting really important today. A lot of things we do today or can be modeled in graph. But can we use relational database technology to do graph? I ask you, use Oracle to model the graph. Will you be able to do that? I would create a table, right, called a node, right, called node 1, node B. And then there's, by definition, an age, and the age with some attributes. Right? I can, if I want to do that, I can create a table of nodes, right? So every node got an ID, and every node got some attributes. I have a huge table of nodes. Okay, easy, right? No problem. And then I create a table called age. Age will be node 1, node 2, and some properties there. It's a friend, or I like you, or whatever, right? That's all. Right? Use relation database is beautiful. I can do anything. Right? You want to model a graph, do it. You have a table for all the nodes. You have a table for all the ages. You have node 1, node 2. Both nodes are foreign key, point to this node table. Right? Whatever attributes you put there, you're done. What is not done is a query. Right? Hey, can you please find whether we are friends, or at least we have someone in between. So we are connected by friendship relation. How do you want to do it? Anyone? You can do it. I'm pretty sure you can do it. Anyone got any idea how to do it? We have two tables. Graph, graph basically is a set of nodes with age relationship. We have one table for all the nodes, and another table for any pair of age, right? Assume we don't care about relationship. And then my query is, give a particular node, A and B. I say, are they connected? How do you do it? I have a table for age, right? I will find the starting point is me, right? You give point A, or say, okay, find this point, start from A. You find a few, right? And then you say, oh, once you find me, you find, okay, what is the next node, right? If you find A, the next node is your friend. You're connected, right? So from A, you end up with a bunch of nodes, which are your direct friend, right? Because you actually linked. So linked such that you have A something actually in the age table. So from A, I found all this linked. But my question is, whether we are linked. So I find from A, I find all these nodes linked, and say, are you inside there? If yes, good, we are linked. If you're not there, I don't know. I say, okay, for each of the nodes, I'm linked to them. I do the same thing. I find all these links to them and see whether you are there, right? So either I find you there, or I exhausted another entire database. I didn't find you. Then I say, no, we are not linked. It's very simple. You can write SQL, but that's iteration. You do it again and again. So you're starting from you search a table, find a bunch of your friends, right? They're all in the table already. And for each of your friends, you expand further, and eventually this friend relationship will exhaust the entire thing. You couldn't find any new ones. Then I say, no, you're not my friend. Also, okay, I found you're my friend. So that's very simple way. But these kind of applications are so important today. I do marketing, social media based. I want to ask a question. I only have $100. I need to employ 10 people to ask them to write a Twitter about my product. The condition is that they can reach most people. They actually really, a lot of people follow them. I want to find 10 person which got maximum influence in terms of different levels of people they follow. Okay, this is question we ask, right? But this question cannot be done using relational database, or it will be extremely hard, inefficient to do it. Key value store helps? Not really. Document store? No. Right? We are talking about different things. Okay. So in this case, what is graph? Graph is very simple. You have a set of nodes connected by a set of edges, right? And the node can have labels. This node is student. This node is a product. This node got labels. And edge got labels. You know, you're my friend. You're my supplier. You're my customer, right? So edge. When you link these two objects together, I can say why we link together. Because I sell things to you, or you know, we are friends or whatever. So that sort of things, okay? And then the query will be that. And then you use relational database, you find is extremely awkward. To handle that, you can, but awkward. Okay, and all these document stores are irrelevant here. So this is the different nodes, different relationship. Each of them got some kind of labels. And then remember, this is scalability issues. We're talking about billions of nodes, right? Billions of nodes. Millions of nodes are easy. Even like Oracle, you know, this lab, they're doing the program debugging. So each of them is a variable, and the procedure call is a link. They can end up with billions of nodes. That's incredible. So Oracle people come to talk us, say, how do we do that? So graph model is very different. You cannot really doing this in relational database. You can use a relational database to store a graph. That's no problem. But relational model just not as suitable for navigation to find information. Okay? So it's not about storage. It's not about the way to use data to answer your query. And in graph database, graph reachability, you know, is there a path with edge from me and eventually reach that particular point? Or find the transitive closures, find traversals. I want to find all the nodes satisfy certain conditions, right? These kind of things, relational databases are not designed for that, right? It's, of course, not really related to aggregate-based. And typically, graph database runs on single node. It's not really running on clusters. It's not saying that people don't want to do it. People do, but it's extremely hard. You can imagine, we do not have a clean way to partition graph such that all the operations will be inside this part, not reaching data that part. If there's paths, link them together, I need to traverse this. So parallelization actually is not very easy for graph database. But a lot of people are doing research, try to use distributed parallel processing to support graph operations. And we mentioned Spark, right? The Spark, there's one library is for graph. The distributed memory to support large-scale graph processing. The dilemma here is that on one side, we cannot partition graph in a clean way that data can be highly localized. If there's a path traverse different nodes, I just don't know where they go. Okay? So on one side, distributing this is extremely difficult, but on the other side, the size of your database is huge, easily dealing with billions of nodes, right? So that's a problem, right? And of course, for our group and many other groups, we say, yep, we do it in large memory, right? So is that 1 terabyte is big enough? Not really, you know, because a lot of 1 terabyte is big enough to store very large data, even billions of nodes. But in order to do this query processing, you do a lot of intermediate results need to be stored. They can be 5 times bigger, right? So it's hard, but there's active research area. So let me end up today's lecture with one system, because all other models we will actually talk more about the systems. But for graph, I just end up with something called a Neo4j. Okay, this actually is industry strength. People do use it. Most people, when they're dealing with graph database today, they use Neo4j. Okay, what is Neo4j? So this is one of the most popular graph database, starting in 2010. So you see that technology today we talked about is so quite recent, right? It's all dealing with emerging things. Developed since 2010. It's open source. It's beautiful. It's Java-based. Okay, they implement in Java, and also you can use in Java. That's what they call it. Is embedded. So Neo4j is graph database. There are 2 ways to use it. One is you embed this into your SQL on the client side. Oh, sorry, SQL. Java on your client side. Okay? So you have a library. When you compile, this database actually is embedded in your Java program. Everything is locally done. Okay? So you can store them and you use them. And of course, there is a server version. Right? Neo4j, like a server, data is there, and you talk to them, you do processing, and to give that data back to you. They're also a version. But Neo4j is very important that it's not only a standalone database server, it is also embedded library, so you can embed into your clients. It's disk-based, right? So the persistency are supported, and they're actually fully transactional, whether people need it or not. Maybe you don't need it, but it's fully transactional, so you can update things, will not cause any problem. So it's a persistent engine that stores data structured in graphs rather than in tables. Right? So this is a Neo4j, and they are optimized for highly connected data. It's not optimized for aggregate data. Okay, this is optimized for highly connected. Right? And then there are a set of basic concepts, which I hope is not very difficult to understand. Instead of they call that age, they call that relation. Of course, something linking two things together, call them relations. Right? So you have a set of nodes, and then you have a set of relationships, which are ages. Okay? And both of them can have properties. Right? You have an age. If you see a friend, what's your trust level? Right? Some are good friends, some not good friends. If you like, we probably also have some attributes, right? So some attributes you may or may not use. But if there are something attributes for the relationship, we call the property of relationship. And for the node, of course, you can also have some properties, right? It's customer, and what is your customer profile, and things like that. Some other properties we can store there. If it is a web page, what will be your content, right? Some properties for this particular node. Right? So these are two basic concepts. And the property, they actually simply use a key-value pair. Because different relationship, different node, they could have very different properties, right? So this is the best thing for us to do is we leverage the successfulness of key-value stores, have ID something there. Okay, they use key-value store to store properties. Okay, they actually claim this is built on top of key-value stores, built on top of document, because it's about navigation. They build on top of our column families, and because they store data also optimized for some kind of access, right? So they believe it's on top of that. And nodes can have labels, right? When you have users, student users, adult users, something like that, right? These kind of labels are grouping nodes into sets, right? Sometimes you only care about a particular set, right? All the users in Australia, right? All the users in university, these kind of labels for these nodes. So they have labels, right, which can group nodes into a set. And then there are two things. These are the two fundamental things they support, relational database cannot support. Because so far, here, it's not a big deal. I can implement using relational database, but it's inefficient. They have two operations. One is can define a path. Paths can be defined. You say, what is the path from A to B? Right? There will be any nodes which got relationship between them, eventually from here to there. Right? And if this age actually got a weight, got a property, for example, its distance between the two users, and I can find the minimum distance, called the shortest path. Right? Or, for example, we have trust level, and then we can aggregate our trust level. So I can reach you, but I want to see what's the trust level between us. Right? So path and the shortest path. Shortest path is just you have some weight on the relationship, and you want to make sure this sum of the weight along the path is minimal. Because when you have point A and B, you will have many ways to reach from A to B. Right? And then if they have age got weights, they will be the different weight. And the one with different minimum weight is shortest path. And the best way to understand it is in road network. Right? All these landmarks, point of interest, they are nodes. And then you have age, whether it's driving distance or flying distance or the cost of petrol cost to reach you or whatever, or the CO2 emission to reach you. this all okay, right? They can do anything. But then we want to find the paths which you either minimize or maximize, which are same. Minimize or maximize, same. Okay, this will be shortest path, right? And another thing is called traversal. You want to have a graph. You want to say from here, I want to reach all the points, satisfy some condition of age, right? Traversal is also important. I want to find 10 people in Twitter, right? I give them each of them $10. They will send Twitter information about my product, and then this information will propagated by followees and followees and followees. And this is traversal. And I want to find how many users at the end can be reached, right? So following that relationship. So these are the operations which are specialized by graph database, right? So because they want to support these applications, and if you want to implement these operations using relational database, that's horrible. You don't do it, right? It's simply take forever to finish. And then they have these ways, and they have special ways to organize them, such that these operations can be supported more efficiently. They have different ways of indexing them. Okay. And then constraint. And these things, they don't have a schema. Any node you can throw into that, any relationship you can throw into that. But if you do have a schema, you tell me what kind of nodes I have, what kind of relationship I have, I can do a better job. So this system is called schema optional. Okay? You don't need to give me a schema so to satisfy your need of flexibility. But if you do want to better service, better performance, and it happen to be you know the types of nodes and know types of age and so on, I can do a better job. Right? So it's optional to you. Right? So Neo4j is really very useful. We can use that to a few million nodes, no problem. Whether they can scale up to billions of nodes is pretty hard. It's pretty hard. Right? So some students in my group just started to use Neo4j. Okay, this is one system. So this is a graphical view of Neo4j, and also that serves as an example of graph database. So what is graph database? They end up with some graph. They manage the graph. They manage indexes. So they are all nodes. And the relationship here called manages, right? And the same thing, you can read it. Okay? All right, that's pretty much conclude today's discussion. We give you a pretty comprehensive overview about all these post-relational things. And one category is document store, 3 types, aggregate model, and one type is graph database. And of course, there's another one called Prego from Google, they design. But then this is open source, so no wonder people use this more frequently. Okay, see you next week.